We have a homework assignment due today. I just passed out some your graded homework from last time. And so as usual, we'll start out seeing if there's any questions on the homework.
Oh yeah, 2.7.
2.7, question 2.7. Oh, that's this.
G, yeah.
G.
Yeah.
Okay. Oh, rats! I didn't bring my book.
That was the same one as C, wasn't it?
What does 2.7 G say? Oh, they are not all true at the same time. No, that's fine.
I'm bringing you my book.
Thank you.
I should have just done it like 2 weeks ago. I'll bring it.
2.7G says they are not all true at the same time. Now I gave you a hint for part E
Right.
here.
You're right, maybe.
So the hint. So tell me for which one. It's the same kind of thing as this hint for part E. It says none or one of the three must be true. So the expression should start like this. Did you understand that one?
Yeah.
Okay. So well, use the same approach for part G. So what does it say? They what?
The following are not all true at the same time. And x less than y.
Oh, actually, yeah, there is even an easier way to do it than following the.
So it's very, very similar to you.
Actually, you now that I think about it, you could do it the same way you would do it for part E, but I think there's even a simpler way than that. Okay, I'll just say it in words. It says they cannot all be true at the same time, right? So how about we rephrase it like this? It is not the case that they are all true at the same time.
Yeah.
Okay.
So, and, not, and.
So break it down. So what expression would you write to say that they are all true at the same time? No, they are all true. In other words, the first one is true, and the second one is true, and the third one is true, right? That's how you would write down. You would write down how they are all true at the same time. It would be the first one is true, and the second one is true, and the third. But if it's not the case that they are all true at the same time, then how do you change that expression to be it's not the case that?
Just a negation.
Okay, so is that, are you with me with that hint? No, there's no. Is that enough of a hint? Okay, let me say it again. All right, do you agree that what the problem says is the same thing as saying it is not the case that they are all true at the same time? Well, I'm rephrasing the question. So to rephrase the question, you could say it like this. You could say it is not the case that they are all true at the same time.
So it's not them being true.
So, well, wait. But now, how would you write down, what Boolean expression would you write down to translate the phrase, they are all true at the same time? How would you write that down? You would write, the first one is, no, no knots. How would you write down, they are all true at the same time? How would you write that down in Boolean algebra? You would do, the first one is true, and the second one is true, and the third one is true, right? That's how you would write that down. So, how would you write down, it is not the case that they are all true?
Negation, and that's the same thing as E.
No, I don't think, hold. Well, maybe, but if you think you found a way to do it, then write that down and hand it in, and we'll see. Okay? So that's your hint. Is that?
Put like equivales true or equals false at the end of all of them?
You don't.
You don't, okay.
Actually, we are going to discover that why today, later today.
Yeah.
That's a very good point, and we are going to discover why. The question was, do we have to put equivales true And the answer is you don't have to put that. You just, in fact, we are going to find out later in just a few minutes, actually, that you don't have to do that. Okay, so are there any more questions about the homework?
No.
One more? Okay, good. I, and this is also 2.7? Okay, and here again, I'm sorry, I don't have the book. So read the problem for me.
I think this one, I like got it in steps, I just didn't get it all together.
Okay.
Okay, when x less than y, then y less than c. Means that b equals to, we're gonna,
Okay, so it's when blah, 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 what?
then y less than z
Then blah, blah, blah,
means that b equals to 0.
means that,
But if,
hold on, means that blah, 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 whatever, okay?
but if
Okay, and now we say, but if
blah,
blah, blah, blah,
then
then,
y greater than z does not hold.
then blah, blah, blah does not hold. Is that the end?
No,
Colon, semicolon,
However,
however,
if then b equals w,
if blah, blah, blah,
then x is less than y.
then blah, blah, blah. Oh, well, look, yeah, it seems complicated, but you just divide and conquer is the strategy. Okay? So first of all, you understand, so let's break this down. You understand but, yeah? And you understand semicolon. They mean and. Okay, so do you remember that? Okay, so basically, oh, and the other thing is, what about, yeah, so this one means and, this one means and, this one means and, right? Now, what about means that? I don't know if we ever actually said means that.
That would be implies, right?
No, it actually doesn't. Means that is equivalence. Maybe we didn't, that one doesn't sound familiar that we went over that.
Didn't do that.
Yeah, well, so that was a good question. This means that is equivalence. Maybe that might have been part of your question. How do you do means that? Yeah. Yeah, actually, now that I think about it, I don't think we did do that, do this example of translating. But that's how you do the means that.
Wait, how? Confused. How? That doesn't make sense.
No. Means that is it's like it defines. It's equal. It's equivalence. Means that that's just the rule. Trust me.
I'm sure you're right.
So just skip it.
But means that, yeah, we didn't talk about how to translate the English phrase means that.
Seems like means that is the same as if then.
Yeah.
No.
If this is true,
No.
this would be true.
Yeah, it seems like this might be implies.
This.
Yeah.
Yeah.
Oh, I kind of see what you're, I see what you're saying. You could interpret it as this means that. But you're not saying that if this is going to happen or if this is true, then this. It means that is equivalence. It means the same thing.
You can take the interpretation, but it goes both ways.
It goes, yeah, it means this implies this, and the other implies this. But that's the same thing as equivalence.
Yeah.
Ah.
Are you with me?
Yep. I get it.
Okay. So now what about when then? Rochelle, what about when then? What about when then? How do you translate this? Yeah, this is implies. When this, so if this is implies, means that this, and then this whole thing has an and. And now if this, then this, but this does not hold. Well, does not hold means what? Negation of this. But this is an if then, yeah. And then we have an and then however, if, what about however? Well, I guess however and semicolon together is just the and, yeah. Because however is like but, So, yeah, okay, so does that help? I think you can,
What is there any does and take precedence over equivalence and
ha ha.
And comes last, doesn't it?
Here it is. Equivalence is way the heck down here and is right there.
so you do the ands first?
Yes.
So that means you need parentheses with that stuff.
Well, you have to make sure that you have to make sure to include any necessary parentheses when you do it.
So you'd need parentheses like
Yeah.
yeah.
Well, make sure that you consult this and put the parentheses where you need them. Yeah? Are we good?
Okay.
All right.
But then with the, when they're all this, when you just have one symbol, then you don't need parentheses at all, right? Because you get the name of the property, but the associative, is that?
Well, yeah,
Like if you just have a bunch of ands, you don't need to have.
correct. Yeah, if you have a bunch of ands, you don't need, yeah. Yeah, it's associativity. Yeah, we will actually learn that in one of our theorems. We'll do the associativity of and. Associativity means if you do the first ones and then the second one that you group. Yeah.
It doesn't matter which way you group it.
Right. That's associativity. That's a really important concept, and we're going to deal with it a lot. Okay? Is everybody good? All right. Well, let's get, we need to get moving here. So if you have any further questions about the homework, just come to me in my office, and we'll clear up whatever further questions you might have. All right, you guys. Now comes this topic. We are going to start proving, and this is the first step of a very long journey. A long journey begins with but a single step. And let's review now what these three properties of equals, or these three properties, is what the proof technique is going to be based on. The first one is Leibniz. If p equals q, then any expression with any variable replaced by p equals that same expression with that variable replaced by q. Second one is transitivity. If p equals q and q equals r, then it follows that p equals r. And the third one is substitution. If p is true in all states, then it follows that p is true with any variable replaced by any expression. It's also true in all states. Okay? So, and we've gone over these and we've had exercises with them. And now we are going to apply them. All right? Now, I have a handout for you. The book has a whole bunch of theorems that it proves, that we're going to be proving. And for your convenience, I have collected them all in one convenient handout. So I suggest that even though you might not want to lug your book around and bring it to class every time, at least always come to class with this, okay? This is going to be your Bible. These are the Holy Scriptures.
The online people doing?
I have one for them too. And also, if you ever lose this, it's available for download. You can download it and print it if you want extra copies, whatever. Or if you want to look it on your iPad, on your iPad you can, electronic, it's PDF. Okay, so, yeah.
We didn't get them handed out to us.
Well, unfortunately.
We should get iPads from this class.
Okay, now, so let's, here we go. Oh, I want to make one more comment that people brought up last time I wanted to clear up. People kept wanting to do truth tables. I want to say a little bit more about truth tables. First of all, truth tables are very limited, and there's two reasons why they're limited. The first reason is this. Suppose we have two variables, p, q, and we want to do a truth table with p, q. How many rows do we have to do the truth table for? 4. It'd either be true, 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 false, false, true, or false, false, right? But suppose you have p, q, r. Now how many rows do you have to have in your truth table? 8 or 9? It's, well, which is it?
Then you get to 4, 5,
It's 8.
6,
It's TTT, TTF, TFT, TFF, FTT, FTF, FFT, FFF, right? Did you count that? 8. How about 4?
16. A lot more.
How many more?
16.
It's 16. And how about 5? How would you like to do a truth table with 32 entries? In fact, This is called the combinational explosion. It's the combinatorial explosion. And it means that each time you add one extra variable to your truth table, you double the number of rows that you have to do the truth table for. So that's one reason. But there's another reason. So not only are truth tables, bad because they get unwieldy because they get so long for complicated expressions, but also there are principles that are involved and relationships between these principles and these concepts that just doing a truth table brute force you don't understand. So there is a structure, there is a logical structure to the theorems and axioms that is hidden by this brute force truth table thing. And it's this deeper understanding that we get by having a deductive system that we're going to embark upon now. All right? So those are the two reasons. So, no more truth tables for the time being. We will occasionally go back and do a few state, figure out what in this state. We'll do that a little bit. And it's important that you know how truth tables work. But from now on, our proofs are going to be based on this deductive system. Okay, so now let's take a look. We looked at a couple of these last time. 3.1 is the associativity of equivales. We discussed that last time. If you do P equivales Q first and then equivalent that with R, it's the same thing as doing Q equivales R and then P equivaling that. Now, the next one, 3.2, is symmetry of equivales. Now here's my question. For symmetry of equivales, why don't we have any parentheses?
It's associative.
Because of 3.1.
Yep.
Once we do 3.1 first, now anytime we have a string of equivales, we know we don't have to do any parentheses.
Yeah.
Because they're unnecessary. That's why 3.1 is the very first axiom. Because once we have that, so what does this mean? This means that for 3.2, it's P equivales Q equivales Q equivales P. Now watch this. P equivales Q equivales Q equivales P. Oh, I'm supposed to use black. So it'll show up on the video. P equivales Q equivales Q equivales P. Now here's the thing, you guys. Because equivales is associative, you could put the parentheses around here, or around all three of these, or around this, or around this. You can put them anywhere you want. That's what 3.1 tells us. Is everybody clear on that?
Yeah.
That's what associativity tells us. Okay? And now, we are going to prove a theorem based on 3.1 and 3.2. Now that we have 3.1 and 3.2, we're going to prove our first theorem. Okay, so here we go. Here's our theorem. Here is our theorem. Our theorem is P equivales P equivales Q equivales Q. That's our theorem. Now I'm going to walk you through this first theorem without asking you what the next step is. And then pretty soon you'll have to contribute more and more to our discussion. Okay? So we're going to prove P equivales Q equivales Q. Now what? And the only things that we have to work with are 3.1 and 3.2, right?
I thought we were proving the third one.
No. The third one is an axiom. You don't prove axioms. I'm going to prove a theorem just assuming that we've only done 3.1 and 3.2.
Oh, okay.
Okay? This is
Which theorem?
this theorem. I'm going to prove this. Oh, actually, yeah. Unfortunately, this theorem is not up there. I'm just making this theorem up. Well, I mean. No, it's not an axiom. We can prove this. We can prove this. And here's how you prove it. Okay? What you do is, now do you remember what's the definition of a theorem? It's either a what or a what?
Either an axiom.
Either an axiom or
Or a theorem that's
Already proved.
proved to be what?
equal to an axiom.
Equal to a previously proved theorem or axiom, right? So what we have to do is we have to start with this. We have to start with this and get it to and get it equal to a previous one. Are you with me? We got to get this one equal to a previous one. So here's how we do it. We start with this. We start with P equivales Q. And now what we do, now I have a suggestion for you now. And I hope you follow this rule. lined papers have a red, most lined paper, they have a red margin line. What I recommend you do is put this next to this margin line, and then when you outdent, make your equals out here, and then when you do your hint, you indent here. And that way, that's a really nice way to do it. Okay?
Why did you write the same thing twice?
Oh, this is the theorem, and this is the proof.
Okay.
Here.
Got it.
So theorem, boom. Proof, we start with the theorem. All right, is everybody clear? Now, we're going to use those three properties that we saw before, Leibniz, transitivity, substitution. Okay, so here we go. Now see if you can follow this. The hint now is going to be 3.2, and what we're going to do is we're going to replace P equals Q equals Q, P equals Q equals Q with P. Now, let's see if you can follow this. Does everybody see that in this expression, this Boolean expression right here, we have P equals Q equals Q? Does everybody see that?
Yeah.
All right. And does everybody see that in 3.2, we have a P equals Q equals Q there?
Oh,
Does everybody see that?
yeah.
We have a P equals Q. But what does that equivalent?
P.
That equals P. So everywhere there is a P equals Q, we can substitute equals for equals and get it to be what? P. So what do? We bring this P equals down, and this one turns into what? P. Now, did everybody follow that?
Yeah. Well, can you write it?
So it's, hold on. So it's P equals P.
Can we just write it with like a textual substitution?
Yeah.
No. This is not textual substitution. This is, there's two separate operations. This is not textual substitution. This is substituting equals for equals, which is different from textual substitution. We're not doing textual substitution here. We're substituting equals for equals. So, and that's a really common, it's really easy to get those mixed up. And you'll have to do it, we'll have to do it a few times before you appreciate the difference. Now, does everybody see this?
Yeah.
This step, how we did that. We're taking this, Q equals, P equals Q equals, and because that equals P, that means we can substitute equals for equals and P. All right, so this equals, because of this. This is the justification. It's called the proof hint. It's this, right? Now, the next step is this. Equals, and the next thing we're going to do is, we're going to do now can you see what we're going to do? We're going to use 3.2 again. Only this time we are going to replace what? We're going to replace this P replace first P with P with what? Yeah, with P. Yeah, with P equals Q equals Q. By the way, it's okay to put your hint on more than one line. You open the hint with this and you close the hint with this. Right? But what happens if now does everybody see why we can replace the first P with P equals Q equals Q? Because P equals Q, well, that's P, right? Are you with me? P. So now we're going to replace this first P with that. So what would we have? When we bring this one down, what does this P, how do we write this P now? Q equals Q. Okay, so this is P equals Q equals Q. Are you with me? But now we still have to do what? Bring down this equals P. Equals, we have to bring this down here, right? And Josh, but now, what is this? Does this look familiar?
Yeah, it's symmetry.
Yeah,
Yeah, it is 3.2. So now we have this equal to this. So now we have to cite that. We have to say which is 3.2. End of proof. Boom, boom. We got 2 slashes here. Now this, hold on. So anytime you, so now we cite, we say, we note, we have to cite, we have to note that this is equal to something that we got before. Okay, so now we're going to end our proofs, we're going to use 2 slashes. Now, I don't know, some books or some, have you ever, you know this? QED. It's Latin for it has been demonstrated. Okay, I forget the Latin phrase. Some books have a box, you know, usually filled in like this to note the end of the proof. But it's easy for us just to go slash slash. Boom, proof is done.
Celebration square.
Celebration.
Question.
Okay? Now,
There are many other ways.
oh, there are many. All roads lead to Rome. I mean, there are literally, I will tell you right now that there are literally an infinite number of ways to prove every theorem.
But not infinite though.
I think there's an infinite number of ways to prove every theorem.
Technically not infinite. I think
No, I'm saying, no, technically infinite. I'm saying, I'm claiming, anyway. And one of the things that we're going to do in this class is we're going to search for good proofs. And the best proofs are the ones that are the what? The shortest. Yeah, or the least writing down stuff. Maybe more steps, but not as, the lazy. We want to be lazy. Yeah,
Yes.
yeah. Now, does everybody see, is every single step of this clear? Is everybody with me on this? Are we good? Okay. Now, so that was an interesting proof. Now let's take a look. Now let's take a look at axiom 3.3. Now, are we going to prove 3.3? Yes or no? Are we going to prove 3.3?
No, impossible.
No, impossible, because it's an axiom.
Why is it impossible?
It's an axiom.
I know, but it is impossible.
No, it's not that it's impossible. It's that we are setting up this system with with a very small number of axioms from which we prove the theorems. Every system has to have a starting point. And this is one of our starting points.
Right.
And because after all, this is the first one that we have that has a constant in it, that has a true in it. So this is defining some property of true.
Right.
Okay? Now, to show you that this
Is
is,
different from the old system?
what old
Isn't that
system?
how you say like this is a new system of logic that we use? Called formal methods. Is that 'cause-
Well, hold on. The formal methods is a new way to, it's a new way to do the proofs. This is called an equational proof style. So it's a new way to do the proofs. But the concepts that we are proving are the same.
Did they start with the same axiom?
No,
Starting point?
yeah, different starting point. Yeah, different starting points and even different techniques for proving. I mean, most people,
Essentially the same.
but it's the same knowledge. I mean, it's the same theorems. I mean,
Right,
the Boolean expressions that are valid, everybody agrees
All the theorems would be.
would be axioms, and other axioms would be theorems. Yeah, but not only that, but the way that they get proved is even different. But still, you're proving the same fundamental. You know, this is what the universe. This is how the universe is made. I mean, these are universal logic truths, but yeah, they just okay. Now, we have the concept of this next one, 3.3, is an illustration of the concept of identity. Have you guys ever heard of the identity element? What is your true identity? The concept of an identity. Now, a Boolean operator, it's possible for a Boolean operator to have what is called its identity element. The identity I of any operator we'll call it circle, is the element that has the property, now check this out, I circle x equals x. Are you with me? On the one hand, and on the other hand, x circle I equals x. That's the definition of the identity. And what is it saying? Why do you suppose we call this the identity? Because if you operate on x with the identity, what do you get? The same thing. And it doesn't matter if you do it on the left side or if you do it on the right side. If you get x, then that I is called the identity. Now let me give you some examples that you're familiar with already.
Zero is the identity of addition and subtraction, and 1 is the identity of division and multiplication.
Yeah. Only it would be, we normally say addition and multiplication, yeah. Okay, so, yeah, that was good. Let me write those down. So, examples. 1 is the identity for multiply. 1 is the identity for multiply because why? Because 1 times x equals x, and what else? X times 1 equals x. Are you with me? So therefore, 1 is the identity for multiply. On the other hand, and what did you say? 0 is the identity for addition. Because why? Because why? 0 plus x equals x, and what else? X plus 0 equals x, right? Does everybody see that?
No.
Did you say no? I was going to say, this is really not high math. That's one of the very first things you learn about addition, right? Is that when you add 0 to anything, you get the same thing. That's one of the very first, that grade school kids. All right, but now tell me, what does 3.3 axiom say? 3.3.
The identity for.
No. For what? You're close, but no cigar. True is the identity for what?
Equivalence.
Yes. That's the operator. Is everybody clear that? Does everybody hear what he said? Okay. This 3.3 axiom says that true is the identity for equivalence. True is the identity for equivalence because why? Because why? No. Because why? Because true equivalence
Times 1.
Q.
Equivalence.
Yeah, let's do the parentheses. True.
Plus 0.
No, not plus. Because true equivalence Q. We'll put the parentheses here to emphasize. Equivalence what? Q. And why else?
And Q equals true equals Q.
No. What else has to be true? What else has to be the case?
Q equals true.
Yeah, and Q equivalence true equivalence Q. Now, how do we know this is the case, though? How do we know?
Associativity.
No. How do we switch? How do we go from here? How do we go from here to here?
Reflexive.
No. Come on.
Symmetry.
Symmetry. Symmetry says. Is everybody clear?
Yeah.
Symmetry. P equals Q. What this says is anytime you have P equals Q, you can that's the same thing. It means the same thing as equals the same. Q equals P. It says you can flip them, right? So that's what we did in going from here to here. Are you with me? So here, let's put, and this is by symmetry. Is everybody clear on this?
Is that why we never have to put true in any of those problems?
Yeah, exactly. Because look what this says. this says anytime you have, this answers your question from before. Anytime you have true equivalence Q, you can just make that Q. Are you with me? So true equivalence anything is redundant.
Yes.
Are you with me? And that has to do with this identity. Is this slick or is this slick? Huh? No. We haven't done false yet. We're gonna get to that. We'll get to false later. Well, I mean that's okay if you don't go through your homework and erase all the equivalence truths if you don't want to, But from now on, it'd be easier to not have to say equivalence true, So you just put yeah. Okay. Is everybody good? Okay. Are you ready for the next proof?
Yes.
All right.
My friend is so excited.
Well, listen. This is like I say. This is the first step of a long, long journey, and it's going to get really interesting. Okay. So here we go. Okay. So 3.4 proof. Now watch this. This is.
We're proving true.
Exactly. Look at this. And I tell you, you try to explain to some your math professor that true is a theorem, and what are you talking? This is very unusual. Because look, 3.4 says true, right? But doesn't have the word axiom in front of it.
What does it even mean?
Well, no, it's a theorem. It's a theorem. And so true. No. So true is a theorem. We're going to prove.
True.
We're going to prove true. And so what do we have to do? What do we have to get it to?
False.
No, don't get it to false.
If true is the
No. What's the rule? No. Hold on. What is a theorem? How do you prove a theorem? You get it to be.
equal to
You have to make it equal to a previously proved, right? So we're going to have to get this to a previous one.
That's easy.
Piece of cake.
Well, okay, hold on. You say it's easy, but let's do it step by step.
Equals Q equals.
Okay, now, so what do we start with?
Substitute Q.
Start with true.
We start with true. Okay, so we'll do true. Now, come on, is this good?
This is so exciting.
This is, okay. So now equals. Now, look, there's only, if we're going to use what went before, there's only one choice that we have, right?
Yeah.
3.3. Okay. Okay. Only hold on. Now we're going to do something. A little bit tricky. We're going to do 3.3 with Q replaced by true.
So there's a notation for that.
Shorthand.
Well, here it is. It's with Q replaced by true. This is textual substitution. Now, with this proof, this is the first proof now where we're going to actually use textual substitution. Okay? Now, here's how this is going to work. Now, watch this.
Is that just for this case? How is this any different than?
No, let me do the step and then you'll see. Okay. So here, true. Now this hint says 3.3 with Q replaced by true. Now 3.3 is a previously proved axiom or theorem, right? That means that we can do textual substitution on it because it's true in all states, right? Are you with me? So here's what we're going to choose to do. We are going to take everywhere there's a Q in 3.3, we're going to replace it with true.
Okay.
Now if we do that, what's it going to look like?
True.
It's going to look like true equivales true equivales true. This little scratch paper on the side here.
Yeah.
Are you with me? You can do this in your head. Okay. Okay. So, so what? So we're going to replace true with what?
True equals true.
True. No. True. We're going to substitute equals for equals. So that true that we have up there is equal to what?
True equals true.
True equals true. So does everybody see that that's how we get this next step? True equivales true.
So now we can just write 3.3 and we just. So say we wanted to just put in like Q equals Q. Can we just write in the note just 3.3?
Yes, you could.
don't need to write dash replaced by-
No, because if you don't, well, in the previous proof that we did, we didn't need to do any textual substitution.
Well, do
We
have-
used,
Do we have to write, like, like replace first P with P?
well, you know, I did that because that was very, if it's obvious, yeah, if it's obvious what you're, but that one, it was a little tricky. Because you had to do one side, and you had to do, you know, it was the first P or the second P. So just to make it clear.
Right,
But here's what's going to happen. In general, actually you bring up a good point. In general, the farther that we get into it, the more steps that we will be able to do, combine and do in our heads. But at the beginning, I think it's really important that you do it this detailed. Okay? Or maybe for yourself. Now, does everybody understand how we did, there's two things going on here. Does everybody understand how we did this step? There's two things going on. First, we did textual substitution in 3.3 to get this, and then we substituted equals for equals in going from here to here. Is everybody clear on that? Okay? Now, what's the next step? Well, we have to get this. Now, can you anticipate this? We have to get this to be equal to something that went before. Well, so does this look similar to something that went before? It looks like 3.3. Well, 3.3 starts with the true equivalence. Are you with me? And this starts with the true equivalence. Are you with me? So this is pattern recognition. So somehow if we can make this into Q equivalents Q, we'll have it. But can we do that?
Yeah.
So how do we do that? So we replace this. So what do we do here? We replace the what?
3.3.
Yeah, replace the second true with what is it? With Q equivalents Q, with Q equivalents Q from 3.3. Boom. And if we do that, we have what? True equivalence Q equivalence Q. And now what's the last step that we have to say? No, we don't do slash slash yet. We don't do slash slash yet because we have to identify. We have to say, we have to cite this, which is 3.3. Is everybody clear? Which is 3.3. Now, boom, we're done.
Oh, yeah.
You're missing equals on the margin.
Fail.
What's that?
You're missing equals on the margin.
Equals, equals, equals.
Never mind.
All right, is everybody, how's that? Okay, let's prove 3.5, reflexivity. Now, can somebody, now maybe you guys can help me do 3.5. Let's do 3.5. 3.5 is an easy one, I think. Okay, so 3.5 proof. What do I write down first?
P equals P.
Good. P equals P. And now, it's a one-stepper. Oh, say, yeah, Kale, what? Say, oh, hold on.
The second P equals Q equals P from 3.2.
Oh, actually, there is a shorter way to do it, I think. You were going to take the second P and replace it with,
Take the second P and replace it with
With
QQP.
QQP. Both work, yes.
That's one step.
what?
It works.
Take the second P and replace it with Q equals P.
Oh, yeah, that's what, but I think there's a shorter way to do it.
Then one
Equal
step.
true. That's true. It's that.
Yeah, that's good. That works. That's good, and it's also one step. But I think there's a slicker way to do it with textual substitution.
3.4.
No,
True.
3.3 with what? Equals 3.3. No, with Q replaced by what? With Q replaced by P.
Do we have to do that every?
Well, if you do a replacement, for now, you do that. Okay, so 3.3 with Q replaced P is what?
But isn't Q just represented
hold on.
Hearing more right now?
Yeah, but this is how textual substitution works. 3.3 with Q replaced by P. So what would this be? This would be true equivals P, right? Right?
Yeah.
So here we have P equivals P. So what is it?
True.
True. And now what do we say? And now what do we say?
Or
Which is?
true.
No, which is?
Which is
3.4. Which is 3.4. Boom, we're done. But your way works too. That was good. That was good insight to see the other. No, but this is really short, see? P, true, boom, 3.4, boom.
I don't have to use textual substitution.
Oh yeah, but you better get, if you don't, he said, if I don't have to use textual substitution, I don't want to do it. But you better get used to it, buddy, because because we're going to be textual substitution, you're going to do textual substitution in your dreams. Let me point out the homework now for next time. Oh, this, you have 4 proofs, all right? So look at your handout here, okay? And it's to prove 3.12 double negation, okay? Here, let me go back to.
So if we don't do this homework, does that mean we can't use these theorems? Because we never proved them?
Okay, now, yeah, that's a good question. We are not going to have time to prove all the theorems, but anytime you have you are assigned to work a proof, the rule is you can assume that anyone preceding that in the list you can use. No questions asked.
Okay.
Because I will tell you that someone has proved all of these theorems in this order.
That sucks.
Actually, I had a student who got really behind in this class once, and he won. I said, well, prove all the ones that you prove them all. Do a notebook and prove them all. And he sat there and he gave me a big notebook at the end. He couldn't do it. He missed a few. Some of them he just couldn't do, but he actually tried it. And but
I'm getting credit for the course.
no, I mean, he needed, well, anyway. So, but I'm telling you, somebody has proved them all. And the rule is, you cannot use the same one that you're trying to prove in a step.
Yeah, right.
You can only use any previous one, but even if you personally have not proved it, you can still use it. Okay, so that's good. All right, so here's what you're going to do. 3.12 for your homework, it's 3.12 double negation. And double negation says what? Not P equivals P. Okay. And 3.13 is the next one, negation of false. So not false equivals true. Okay. And then 3.14, P not equivalent to Q equivals not P equivals Q. And then 3.19, mutual interchangeability. P not equivals Q equivals R equivals P equivals Q not equivals R. Now, there's one more technique that you really I need to mention, and unfortunately we don't have time to demonstrate it. But I want to mention it. In the book there's a 3.6, a proof method, that says to prove that P equivals Q is a theorem, transform P to Q or Q to P. And I want to give you a hint on this last one. So for 3.19, here's a hint to prove 3.19. Do not start with P not equivals Q equivals R equivals P equivals Q does not equivals R. Do not start with this and get it to a previous. And get to previous.
Wait, what?
Do not start with this and get it to a previous. Okay? Instead, do this. Instead, start with P not equivals Q equivals R and get it to what?
Get it to the same as the other.
And get it to this. Anytime you have a theorem that has an equivalence in it, you don't have to do the whole thing and get it to a previous one. You can do one side and get it to the next side.
Okay.
Are you with me on this?
Wait, is that the same as proving it?
That is the same as proving it. That's a proof technique that we'll discuss more in class on Monday.
So at the end, what would we like?
No, at the end, now at the end you don't have to say which is. Now you can just do boom boom because you got this to this boom boom. All right. So in fact you cannot cite it because this one's not a previous, that one's not a previous one, right? All right, good deal.
But say like the first one on our homework is 3.12. We can still use 3.8, 3.9, and all that for proving 3.12. Yeah.
Oh sure. To do 3.12 you can use 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right.